So reflecting functions. Something we've already seen a little bit of when we're talking about odd and even functions, or at least even functions. But let's kind of do the same thing as before. Let's have the setup. Let's make our lives much easier than the last example. I don't know, let's have this as my function. It's basically the same, isn't it? Let's just do this. So there are two very simple reflections I can see here. One of them would be reflection in the x-axis. One would be reflection in the y-axis. So if I was to reflect this in the x-axis, what would it look like? So, oh my goodness, this is really hard to draw cold. Just have to think about this. Is there some clever way of doing this? Nope, I'm going to have to do it like this. It's not too bad. That would be reflection in the... I can do a bit better than that. Or maybe not. Let's see. There we go, it's a little bit better, I think. So that is reflection in the x-axis, and then of course we could reflect on the y-axis. So reflecting on the y-axis, what would it look like? Well, it would look like this. Higher up. Not so bad. That's the reflection in the y-axis. So we want to know actually what happens to the functions here. So it turns out it's really simple, and it's not completely unrelated to what we saw with even functions. So let's move this down a little bit and then just introduce the possibilities. So first of all, blue, that was the reflection in the x-axis down here, wasn't it? And that's actually a very simple way. So first of all, that's a translation, that's a vertical change, isn't it, right? So it turns out that again is some sort of change in the input. So if I have y is equal to minus f of x, this is exactly what you'd expect. This is the graph y equals f of x reflected across the x-axis. Reflected over or across, it's up to you how you wanted to say it. So down here, this is y is equal to minus f of x. That's pretty obvious, really, right? You can see you're just replacing the height with negative of the height, so it makes a lot of sense. Now, if I want to reflect in the y-axis, well, that's a change in the horizontal, so it actually has to be a change in the input, and it's kind of what you'd guess. Y equals f of minus x. So I'm changing the input now. This is equal to y of f of x reflected across the y-axis, which is a horizontal change. So down here, this is what my y of f of minus x is. And again, just to reiterate, here we're altering the entire output. Output is being changed for minus the output. That's the change we're making. And here, the change is, well, it's an input being changed for minus the input. So it's kind of like a composition where I'm kind of composing with minus x if you want. Okay, nice. So this reflection in the x and y axis, this corresponds to something very, very simple when it comes to the actual formulas for the functions. Namely, you're replacing the output by minus the output for a reflection in the x-axis, and you're replacing the input with minus the input for a reflection in the y-axis. Okay, You can also see why this is related to even functions, right? Because for an even function, what's the deal? An even function is one, so just here, where this is equal to f of x. That's what even means. So what that means is the graph isn't changed when I reflect it in the y-axis, which is something we saw at the very start when we were thinking about symmetry of functions. So it kind of fits together quite nicely. All right, so in all of these three cases, we're getting the same kind of pattern emerging. So important observation. So important observations. Changes to the output give vertical transformations. That makes a lot of sense, doesn't it? Because the vertical is the y-coordinate, represents the output of the function. However, changes to the input give horizontal, and that makes a lot of sense because the input is the x-axis, which is the horizontal. So changes to the input give horizontal. Give horizontal transformations. So things like horizontal transformation left, right, all the rest. Now, this is all well and good, but there is an easy notational confusion in this. So when I say the output, I mean the whole output, the output of the function, whatever it is. So this doesn't seem too important when you first see this, but it's really important. So when you're talking about the function f of x, and you've got it written, and you've got your actual expression on the right-hand side, whatever it is, it could be x squared plus 7 divided by 19. The output is everything on the right-hand side. So whatever you're doing, multiplying it by a constant, adding a constant to it, multiplying it by whatever minus 1, it's got to be the whole right-hand side which is changed. So this is a bit confusing if I don't give an example, but I will do in a second. The input, though, a bit simpler, that's always just the x. Right, that is the input, right? That's the way everything is set up. So let's do an example, just to illustrate why you've got to be ridiculously careful. So let's do, shall we do, yeah, I'll do one that's a bit difficult, just to illustrate what I mean. So imagine I give you a function in a bit of a weird way. So imagine I've got the graph y is equal to f of x plus a plus 2. So it's almost like I started with y of f of x and I've messed around with it a few times. But let's imagine this is how the function is given to me. So the function is f brackets of x plus 5 plus 2. That's what the function is. So when I read this, I read to myself, okay, this is, remember x is the input, so this is f, so this is really going to f of the input here, plus 5 plus 2, and the output is the whole thing. Everything is the output. It's easy to get confused and think the output is just this piece, just because of the way the notation was set up before, but no, right? The output is the entire function. The y is the output. So let's do two transformations, just to show you why you've got to be very careful about this. So two transformations. So let's do one first of all, which is a horizontal compression by 2. That's a good one. Horizontal compression by a factor 2. So what does that do? Well, how do you do that? You have to replace the input with 2 times the input. Horizontal compression is always multiplication by that. So what am I going to do? Well, that would mean I would need f of, sorry, I should write y is equal to, so this is my new thing. So it'd be f of Okay, so now all I'm going to do is replace the x with 2x. So I'm just going to really carefully write this. Plus 5 plus 2. So you see there, all I'm doing is replacing the input. The input is replaced with, so I should do it with a straight. The input is replaced with 2 times the input. That's the input, that's x alone. Now, a warning, a mistake I've seen countless times. Disastrous in midterms. This is not equal to the following. So the input is x. The input is not x plus 5. Sure, you're feeding that into your function f, but f isn't the function. The function is this whole right-hand side. So a really major error is thinking, okay, it's just going to be this. You just multiply whatever's inside f by 2, all good. It's not that. And I can show you why it can't be this, because this is equal to f of 2x plus 10 plus 2. And that don't match up. They're different. So when you're doing any horizontal, anything horizontal, it's only the x which is being replaced. It doesn't matter how it's been presented to you. Whatever x is, you just replace it with the appropriate thing. In this case, where horizontal compression by factor 2, you replace the x by the 2x. Okay, so this is a warning. You don't replace what's in the brackets for f, it's wherever x turns up. Wherever x turns up. I can't stress this enough. If this is confusing to you, and it is pretty confusing, like pause the video, take the time to kind of sit and really think about what I'm saying here. It's really important you understand this. If you don't understand this point, it will have a terrible knock-on effect when you're trying to do more complicated combinations of transformations in the next video. So let's do another one, but let's do a vertical one. So let's do a vertical stretch by factor 2. Let's do this one. So what does that mean? Well, vertical stretch by factor 2 involves multiplying the output by factor 2. So it would be y is equal to 2 multiplied by the entire output. That's this. The whole thing. So in particular, if I was to kind of factor this out, this would be 2f x plus 5 plus 4. Warning. Again, a massive mistake people make. They just think, okay, I'm just going to multiply f by 2, end of story. So that's not what's going on here. It's the output that matters. So again, a warning. This is not equal to 2 multiplied only the f piece. Of course it's not, right? You've got the 2 and the 4 out. And the mistake that's being made here is the following. It's this. This is not the output. Not the output. The output is the entire thing. This is the output. As I write just over here. And the mistake up here, again, same thing. This thing, this is not the input. The input is the x, not the x plus 5. You are putting x plus 5 into the function f, but as I said, it's not f. It's more than that, right? It's f of x plus 5 plus 2. That's the function. This is your function. So this is one of these things that's confusing about notation, because you've had this explained to you with f notation. So if I write this down with an f which has been messed with, it's no longer applicable. You've got to think purely in terms of inputs and outputs. So this is just something important because it causes terrible problems. So there we go. When you are doing these horizontal and vertical changes, horizontal, you are changing the x alone. X alone, it's the input. Vertical, you are only changing the output, the entire output. You're changing the y. Right? You're not just changing, you're changing the whole thing. You're not just changing a little piece of it. It's the entire thing has to be multiplied by a constant or whatever, right? Depends on the circumstances. So very, very important. And in the next video, you're going to see why this is so important if you're going to do a collection of these transformations one after the other.